Now I'm going to take a laminate material and see how it behaves when it's part of a structure. The structure is a simple plate, so we're going to do a plate analysis. The laminate I'm going to use is one I've created earlier. It's slightly more complex than the little cross-ply laminate we had here. Quasi-ISO CFRP is an 8-ply laminate made of unidirectional carbon epoxy plies again, but with some 45s in here as well. The ply thickness is the same as before, so the total laminate thickness is only 1 millimetre. Remember that this is a material, it's not yet a structure. We can put this material into a simple plate. Let's take something that's 1 metre wide and 2 metres long. So there's a rectangular plate. Notice we can't change the thickness of the plate because that's defined by the laminate. If we want a thicker or thinner plate, then we have to modify either the ply thickness or the number of plies in the laminate definition. In bending, we have 3 alternatives for load types and boundary conditions. These are fairly self-explanatory: uniform or concentrated loads and simply supported edges or clamped edges. Let's take a uniform load, simply supported edges of just 100 pascals, 100 newtons per square metre, and we'll look at the deflection in the centre of that plate. So that's going to be x equals 0.5, y equals 1. That'll be where the maximum deflection is. These numbers here, m max and n max, are used in the solution process. Essentially, the higher these numbers are, the more accurate the solution is going to be. We'll leave them at 10, which is a reasonable default value to use. Then we're ready to hit calculate, and we get some information about how that plate is expected to behave. What we're most interested in is the deflection. This is the deflection at the centre, 1.65 times 10 to the minus 1 metres, so that's 165 millimetres, quite a large deflection, because of course the plate is very thin. We also have a calculation of the bending moment. The other tabs here are concerned with stability, so we can calculate a critical buckling load when the plate is subjected to in-plane compressive loading. And the final tab there will calculate vibrational modes. We get the fundamental frequency, the lowest natural frequency of the plate. Now you might think that's not a particularly good way of designing a plate in bending. We have quite a large deflection here in a rather thin plate. Normally when we're looking at bending stiffness, we would want to include a sandwich structure of some kind. So let's see how well the plate does if we make it into a sandwich. The sandwich analysis tab will use the laminate that we've chosen as the skin of a sandwich. So here's the quasi-isotropic 1 millimetre thick carbon skin. Now we're going to combine that with a core material. So let's put in the same panel dimensions, 1 metre wide, 2 metres long. Core thickness, I'll go for just 15 millimetres, 15 E-3. The face thickness of this sandwich is determined by the laminate. As we've already said, that's 1 millimetre. Here we have lots of alternative core materials already in the database. Again, some of these may look familiar, some of them won't. Let's, just for demonstration purposes, pick the high density foam, and that's defined a laminate for us. We can put that sandwich laminate into a beam. Again, this is fairly self-explanatory. You have a range of load types and support types. And in the panel bending, just to compare with our previous example, let's put in 100 pascals again on the panel, and we can calculate a deflection, and this has fallen right down to 0.14 of a millimetre. So by making our panel thicker, it has a sandwich panel, we've reduced the deflection considerably. With sandwich structures, there's quite a lot of other information we need to know when it comes to considering strength. We need to know the stress in the faces of this sandwich sheet. We also need to know what the shear stresses are in the core, because sandwich panels can have potentially complicated failure modes. Again, we'll come back to these aspects a little later on.